All right, welcome back. Today's lesson is arithmetic sequences. And up to this point, you've probably thought that a sequence is just a list of values in which you find the next number. And let's look here. So we have -3, -1, 1, and 3. This is an example of an arithmetic sequence. And notice the values are increasing by 2. So if we want to guess the next number, if we increase 1 by 2, we get 3. Increase 3 by 2, we guess that the next number would be 5. And which is true. However, sequences are far more than just a list of values. Okay, so let's first define what a sequence is. So go ahead and get your definition sheet out. I'm going to give you both definition of sequence and today precise definition of what a function is. And secondly, you're going to need graph paper to take notes on this lesson. Okay, so first definition sheet, definition of a sequence. What is a sequence? Okay, so first, a sequence is a function. Okay, so it can be graphed. A sequence is a function whose domain is the set of natural numbers. Okay, a set of natural numbers. The set, not a set. The set of natural numbers. Numbers that are simple numbers. Okay, so let's look at what the set of natural numbers is. Capital N with 2 lines represents the set of natural numbers. Okay, so I'm just going to give you an example here. Okay, well, we're going to write the set of natural numbers, capital N with 2 lines. These are the simple numbers, that counting numbers, okay? So we're going to leave out, I'll show you. Okay, so the set of natural numbers, 1, 2, 3, 4, 5, ... Okay, so the counting numbers, simple numbers, big gaps in these numbers. Okay, big gap to get from one number to the next. 1, 2, 3, 4, 5. Okay, first question is, are there negative numbers in the set of natural numbers? No. Natural numbers are just positive. Okay, secondly, is 0 in the set of natural numbers? No. Okay, the natural numbers are just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers, the counting numbers. Your age is an example of a natural number. So let me put this on the board. This number line is going to help us understand. Okay, so we're going to call this the x-axis, and we have, let's see, here's 0, 1, 2, 3, -1, -2, -3. And the natural numbers. Natural numbers are just counting numbers. 1, 2, 3, so on and so forth. Does this set go on forever? Yes, but notice there are big gaps. Okay, we've talked about a lot of numbers, or we've talked in previous lessons about there being a lot of numbers between 1 and 2, a lot of numbers between 2 and 3. For instance, 2.5. Is 2.5 between 2 and 3? Yes. Is 2.55? Yes. Is 2.56? Yes. What about 2.6, 2.7? Yes. There are many, many, many numbers between 2 and 3. So if we look 2, 3, how many numbers have we left out? Okay, have we left out 2.1? Yes. Have we left out 2.2? Yes. We're skipping, okay? So we're skipping a lot of numbers. In fact, we're skipping infinitely many numbers between 2 and 3. Now, before we get into this more, I just need you to see for now, natural numbers are positive, their counting numbers do not include 0, and they do not include negative values. Before we go further, let's go ahead and define what a function is. Okay, so definition of a function, and this is the most important definition in this class. Okay, it's going to take us a while to develop what this definition actually means. Okay, so definition of a function says a function is a set of ordered pairs in which each element of the domain maps to exactly one element of the range. Basically what this definition is saying, I don't know if you've ever heard of, okay, if function is a set of ordered pairs in which each element of the domain maps to exactly one element of the range. I don't know if you've ever heard of vertical line test, but vertical line test is a visual way or a geometrical way of understanding what a function is, or actually be able to test to see if a set of ordered pairs is a function, meaning that if a vertical line crosses more than one point on a set of points, and the set of points would not be a function. But in your notes, a couple of weeks ago, I gave you a definition of a function, that a function is a machine with an input called the domain and an output called the range. It's not wrong, but it's not precise. So I want you to erase that old definition of function, the first definition. Think of that as a beginning definition, not a precise definition. But the precise definition of a function is that a function is a set of ordered pairs in which each element of the domain maps to exactly one element of the range. And throughout the semester, I can say this is the most important definition in this class. Your goal in this class is to understand what a function is. But this will be developed later. What I need for you to know right now is I should just say, memorize this for now. Okay, now element is a word for number. Okay, so I'm going to reread this maybe to make it a little more clear. A function is a set of points. Okay, so ordered pairs are just points on a graph. A function is a set of points in which every number, each is every number in the domain maps to exactly one number in the range. Okay, so in the next lesson, I will try to give you a little bit of a visual of what this definition is saying. But for now, I just need you to memorize this and erase the old definition of a function out of your notes. Okay, so this is the precise definition of what a function is. And throughout this course, we're going to be looking at what this definition means. All right, now, but today's definition that we need to focus on is definition of a sequence. All right, now, I'm going to erase the definition of a function off the board. And we're going to look at definition of sequence and this set of natural numbers. Okay, so natural numbers, we've been working up to this point in the set of what we call real numbers. Okay, the real numbers down here, capital R with two lines. All right, we're going to look at this in a moment. What's the difference? Now, before we get to the real numbers, let's look at the set of integers. Okay, set of integers is the set of numbers. Dot, dot, dot means it goes on forever. -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. Okay, so again, goes on forever. Okay, so the set of integers. Does the set of integers include the natural numbers? Yes. Okay, notice 1, 2, 3, etc., 4, 5, 6, 7, 8, 9, 10 are the set of natural numbers, or is the set of natural numbers in the set of integers? Yes. Notice that the set of integers includes all of the natural numbers, their opposites, -1, -2, -3, and includes 0. Okay, so notice the natural numbers do not include negative numbers. The natural numbers do not include 0. Okay, but the integers do. Okay, so the integers include all the natural numbers, 0, and their opposites. My question is, which of these two sets has more numbers? Which of these two sets, the natural numbers and the integers, which one has more numbers? I was asked this question when I got to college, and I immediately said the integers. The integers have more numbers because it's not only the natural numbers, but it's also all their opposites and 0. But in fact, this will blow your mind, these two sets of numbers have the same number of numbers. And in order for you to better understand the definition of function tomorrow, I will show you how does the set of natural numbers have exactly the same number of numbers as the set of integers. Well, one way to think of this is that both sets go on forever. So which one has is there a difference between one infinite and another infinite set? Okay, is there such a thing as a bigger infinity? Okay, so we agreed that the natural numbers never stops. Is 100 a natural number? Yes. Is 101 a natural number? Yes. Okay, so we see that the natural numbers have an infinite set of numbers. So does the integers. Okay, so both sets have an infinite set of numbers, or infinite number of numbers in the set. Kind of intuitively, it kind of makes sense that infinite is the same as infinite. But just looking at it, it doesn't seem to be the case. Okay, so I will show you in the next lesson why these two sets have the same number of numbers. And in fact, we use a function. We use the concept of function, not sequence, but we use the concept of function, the definition that I wrote on the bottom, to show this. Okay. Now, the real numbers. Okay, so the real numbers include every number you can ever think of. So my question is every integer a real number? Yes. Okay. So let me say it like this here. These were the natural numbers. I made these points, 1, 2, 3. The set of integers not only includes 1, 2, 3, but it includes 0, -1, -2, -3, and goes on forever. But again, are there gaps? Are there gaps between the points? Yes. The integers have a gap. Is 1.5 an integer? No. Is 2.7 an integer? No. Integers do not include decimal values, if you want to think of it that way. 2.75 is not an integer. 2.75 is not a natural number. So if we look on the number line, 2.75 between 2 and 3. Is 2.75 an integer or a natural number? No. Okay, so we're not including, there's a big gap between these numbers. But the real numbers include every number you can ever think of. So think of this as connecting all of your points. This goes on forever, the entire number line. Okay, so does the real numbers include all the integers? Yes. Does the real numbers include 1.5? Yes. Do the real numbers include 2.3 repeating? Yes. Okay, do the real numbers include numbers like pi, what we call irrational numbers? Yes. Here's something that'll blow your mind. Again, pi is equal to, you guys know this is 3.14, but it is not. Is pi 3.14? No. Is pi 3.1415? No. Is pi 3.141592? No. Okay, this number pi goes on forever and ever and ever and ever and ever and ever and will never, ever be able to be written. No human, no computer will ever be able to write this number. Why? You write it out to 500 places, 600 places, 1,000 places, 1,000,000 digits beyond 3.14. Have you written the number? No, the number goes on forever. So we get way down here, okay, way down here in the number. If we switch one digit in the decimal, so we switch a 4 to a 3, we have a completely different number. If I take this 2, 3.141592, and switch it to a 1, do we have a completely different number? Yes. Okay, so how many numbers are there just next to 3.14? Infinitely many. And since we can never write the point 3.141592, okay, we can never write this value pi. It goes on and on forever. We use a symbol to represent it, pi. Okay, so these numbers that go on forever and ever and ever. Pi is an irrational number, a digit or a decimal that goes on forever and never repeats. What about square root of 2? Yes, this is also a number that goes on forever and ever and ever and never repeats. Numbers like e, okay, we're going to talk about e later this semester, numbers that go on forever and never repeat. Okay, what about 156.3 divided by 2.7? Is this a real number? Yes. Real numbers include any number you can ever think of. Or let me say it like this, every number on the number line. So connecting every number between 2 and 3, every number between 1 and 2, every number between 0 and 1. Okay, so it forms a solid line. Now, my question is, which of these two sets, the integers or the real numbers, have more numbers? Okay, and we said up here that infinite was the same as infinite, but that's not the case. In fact, the real numbers have far more numbers than the set of integers. What? Okay, so now it starts to, this starts to get weird. Okay, so this infinity down here, okay, we know that there are an infinite set of numbers and the set of real numbers, is a bigger infinity than this infinity that represents the numbers in the set of integers. Okay, so now we have levels of infinite. One infinity is bigger than another infinity, whatever infinity is, forever. But these kinds of things will blow your mind. It just starts to get weird. Okay, so if you want something, this is better than sleep medication. This will put you to sleep at night. Okay, so if you just start thinking about this, either it'll drive you nuts. Well, obviously this. For me, I lost sleep. Okay, it drove me nuts. Okay, I lost sleep over this. But for you, maybe if you just think about this, it will put you to sleep at night. So you can think of this as weird stuff. The natural numbers and the integers have the same number of numbers, but the real numbers have far more numbers than either of these two sets. Okay, so enough of this. For now, what I need you to know is that the set of natural numbers, in the set of natural numbers, we are skipping a lot of numbers. Okay, we're just looking at what? 1, 2, 3, 4, 5, big gaps. Is 2.5 a natural number? No. Okay, so natural numbers. Why? Because we're going to be looking at sequences, and the domain of a sequence is a set of what? Set of natural numbers. Now, starting with this sequence here, okay, so I want you to take this and circle it. Okay, the sequence that you're looking at, this is the range. The range of what? Now, we've talked about domain and range. It's the range of the function. What is a sequence? A sequence is a function whose domain is a set of natural numbers. Up there, we circle this. This is actually our range. Now, underneath -3, I want you to write a sub 1. Underneath negative 1, a sub 2, a sub 3, a sub 4, and let's talk. What is a sub 4? A sub 4 is a concept of position. Subscript 4 means position 4. So at position 4, what is our value? 3. At position 3, what is our value? 1. At position 2, what is our value? Negative 1. 4 has no mathematical meaning, or I should say no operational meaning we're not multiplying by 4. All this means a sub 4 is read as a subscript 4, which means position 4. Okay, more precisely, a sub 4, we're going to think of this as height at 4. Okay, so if I ask you, what is the height at 4? What is the height at 4? Height at 4 is 3. Okay, if I say a sub 2, what are we saying? Height at 2. Okay, so what is the height at 2? The height at 2 is negative 1. Okay, and what if I say a sub n? Okay, a sub n is the height at n. Okay, so a sub n is height at any number n. Now, let's start. So sequence. The first thing you guys have to do is to calculate a common difference. Okay, what is common difference? Okay, well, arithmetic means something is being added. Okay, what is being added? What is being added? The common difference is what is being added. Or we think of common difference as concept of slope. Now we've talked about slope with respect to linear function. For now, before we get to slope, let's think of common difference as what is being added. Okay, so I'm going to erase this. So a sub n, again, a sub n is thought of as height at n. Okay, at any number n. So, okay, going back to common difference. Common difference is variable d. Okay. And variable d represents what is being added. What is being added? To get from number to number in the range. To get to the next number in the range, what are we adding? Well, you can look here and see what is being added to get from negative 1 to 1 or from 1 to 3. We already established this earlier, that 2 is being added. So our common difference, or d equals 2. But how do you find this if it's not obvious? It's not always easy to look at a sequence and tell what the common difference is. So if you were trying to find common difference, this is what you do. You take the second value. In this case, the second height is negative 1. Okay, so take the second value, negative 1, and subtract the first value, negative 3. So take the second, subtract the first. Take the second value, subtract the first. Think of it this way. What are we doing to go forward? To go to the right, what are we doing? Okay, we're adding 2 to go to the right. To go to the right is to add 2. So to go backwards is to do what? To go backwards is to subtract 2. Okay? If you're trying to find what's being added, okay, you will subtract. Okay, so take the second value, subtract the first. Negative 1, subtract negative 3, minus negative changes to add. Okay, so we get negative 1 plus 3, which is 2. So our common difference is 2. Okay, this is important. It's going to be thought of as slope. Okay, now step 2 is to graph. Okay, step 2 is to graph, and we're going to construct a t-table. Okay, instead of x and y, we're going to use n and a sub n as our variables. N and a sub n. This is just convention. All right, now in our graph, we have the n-axis. We also have the a sub n as our y-axis. Okay, a sub n. And now we're going to write, what is the domain, the input? Okay, remember that the input is called what? Input is called domain. Okay, and we know what is the domain. What is the domain of any sequence? Whether it's arithmetic, we're going to be studying geometric, or any sequence that you can think of, it does not matter. What is the domain of a sequence? The Mars sequence, outer space sequence. Okay, so what is the domain of a sequence? Regardless of what sequence you're looking at, the domain is what? The set of natural numbers. So we already know what our domain is. Okay, up to this point in this class, you've regarded domain to be any real number. Any number could be in the domain, not with sequences. With sequences, the domain is very specific. The domain is always the set of what? Natural numbers. So we say the domain is what? 1, 2, 3, 4, and nothing else. Put dot, dot, dot. Okay? So we have big gaps. Is 1.5 in the domain? No. Is 2.7 in the domain? No. We're skipping all the numbers between 2 and 3. Okay? Put dot, dot, dot. This set goes on forever. You're required to graph the first 4. the first 4. So you can think of domain 1, 2, 3, 4 as position. I'm circling it. A sub 1 means height at 1. Okay, 1 is your domain. 2 is your domain. 3 is your domain. 4 is your domain. Or position 1, position 2, position 3, position 4. Now we want to put our range. Okay, so remember output. The right side of the t-table is range. Okay, and the range is already circled. The range is the list of numbers that you were looking at. Okay, so our range here is what? -3, -1, 1, 3, ... Now I want you to notice, in the range, can we have negative numbers? Yes. Okay. In the range, can we have decimal values? Yes, possibly. Any real number is allowable for the range. Okay, you can have any number or any real number. Could pi be in the range? Yes. Okay, but is our range the set of real numbers for this function? No. Okay, there are still gaps. There are still gaps between -3 and -1, between -1 and 1, between 1 and 3. Notice 2 is not in the range. Okay, so the range is not all real numbers, but we say that the range could be. The range could be any real number. Any real number is allowable for range. But our domain is specifically, this is where we're focusing, domain is specifically what? The natural numbers. Okay? Are there negative values in the domain? No. Are there decimal values in the domain? No. For instance, 2.5. Absolutely not. Now, what we end up with here are ordered pairs that we can graph. So we're going to graph this. This needs to be done on graph paper. Okay, so you're taking notes on graph paper. And I say this to students. Do not change the scale of the n-axis. Do not change the scale of the n-axis. Why? Because your n-axis or your domain will always be natural numbers. Okay? Natural numbers starting at 1, 2, 3, 4. Okay? So we're not going to have to change the scale. This scale will always be in units of 1. 1, 2, 3, 4. And this will be the same for every sequence that we graph. However, your vertical scale, I tell students, change the vertical scale or let your vertical scale match the common difference. Okay, so since our common difference is 2, let's make our vertical scale units of 2. So 2, 4, 6, 8, 10. And the negative scale will be the same. Okay, -2, -4, -6, -8, etc. Now, let's go ahead and graph our points. 1, -3. 2, -1. 3, 1. And 4, 3. Now the first question is, do we connect the points? Do we connect the points? No. Do not connect the points. Okay, do not connect the points. Why? Well, do the points form a line? Okay, do the points form a line? Okay, when you graph a line, how many points are you graphing when you graph a line? You're graphing infinitely many points. Infinitely many points stacked infinitely close together. We've talked about this. Infinitely many points stacked infinitely close together. Is a sequence a set of infinite points? Yes. But are the points stacked infinitely close together? No. Why not? Because our domain is what? Just 1, 2, 3, 4. There are gaps in the domain. Look. For instance, what if, okay, or I should ask, is 2.5 in the domain? No. Okay, so what if, I'm just putting this, what if 2.5 was in the domain? Well, if 2.5 were in the domain, we would have a y value of what? Probably 0. Okay, this is not a point in the function y because 2.5 is not in the domain. Let's find the point on the graph. 2.50 would be where? 2.50 would be here. Now my question is 2. I'm going to erase 3, 1. Put 3, 1 down here. Okay, is 2.6 in the domain? No. Okay, 2.6 we would have, well, 2.5 was 0. Okay, so every gap, every point 1 is 0.2. So 2.6 we would have 0.2. Okay, so at 2.6 do we have a height of 0.2? No. At 2.6 do we have a height of 0.2? No. Why? Because 2.6 is not in the domain of the function. 2.6 is not in the domain of the function. So do we have points line at 2.5, 2.6? At 2.7 do we have a point? No. At 2.4 do we have a point? No. At 2.3 do we have a point? No. Do we have infinitely many points between? Absolutely not. There's just empty space between. There's nothing between any 2 points. Why? Because our domain is just what? Broken points. Broken points where? Broken points why? Because the domain is just natural numbers. We just have a point at 1, or we have a height at 1, Okay, again, we read this as height here. What is height at 1? Height at 1, we read a sub 1 as height at 1. Height at 1 is what? Height at 1 is negative 3. At 1, we have a height of what? Negative 3. Looking at 1 on the on the n-axis at a height of 1, or at 1, what is our height? At 1, we have a height of negative 3. Notice height at 1 is negative 3. At 2, do we have a height? Yes, at 2, we have a height of negative 1. Look, at 2, we have a height of negative 1 down here. Okay, at 3, do we have a height? Yes, at 3, we have a height of what? 1. At 3, on the n-axis, we have a height where? At 1, meaning there is a point at 3, 1. Okay? Also, at 4, do we have a height? Yes, at 4, we have a height at 3. So at 4, on the n-axis, we have a height at 3. Creating points that are located at 1, negative 3, 2, negative 1, 3, 1, and 4, 3. But there's nothing in between. Why? Because there are just, or I should say, the domain is just what? Natural numbers. Okay? Now, question. We don't connect the points. We don't connect the points, but do the points go on forever? Yes, the points will continue forever. So do we put an arrow like this? Do we put an arrow to indicate that the points go on forever? No, this looks silly. Okay, we don't put an arrow, so how do we indicate that the points go on forever? The dot, dot, dot in the t-table indicates that this pattern continues forever. So think of the dot, dot, dot as representing an arrow on the graph. Okay, so the dot, dot, dot indicates that the points go on forever in the same pattern. This is not a line, but we call this a linear pattern. And we are actually going to use what we know about linear function to investigate the arithmetic sequence. Okay, so arithmetic sequences can be thought of as related to linear functions. So everything you learn about linear function is going to be used to study what? Arithmetic sequence. Okay, so this is a broken set of points that follow a linear pattern. My question is, are there ever going to be points to the left of the y-axis? Or are there ever going to be points to the left of the a sub n axis? No. Why not? Is negative 1 in the domain? No. Remember, domain is your x-axis, or in this case, n-axis. Is negative 1 in the domain? No. Is negative 2? Is negative 3? Is negative 4? No. Are we going to have a height at negative 3? For instance, are we going to have a height at negative 3? No. Because negative 3 is not what? Negative 3 is not in the domain. So we're not going to have a height at negative 3. Since we don't have negative numbers in the domain, there will never be points that lie to the left of the y-axis. Also, question, is there a point that lies on the y-axis or the a sub n axis? Is there a point on the y-axis? What would we call a point that lies on the y-axis? We would call that point a y-intercept. So my question is, does an arithmetic sequence have a y-intercept? Okay, so we're writing y-intercept, question mark. Does an arithmetic sequence have a y-intercept? No. Why? Well, let's look. If this pattern continued backwards, or let's look up here. We have a sub 4, a sub 3, a sub 2, a sub 1. What would this imaginary, this is not a point, but I want you to write it on your paper. A sub 4, 3, 2, 1, write a sub 0. Okay, a sub 0. Is this a point in the function? No. Why? Because 0 is not in the domain. So I'm going to put 0 here in the t-table. Put 0 in the t-table, and let's figure out backwards. 3, 1, negative 3. If we're adding 2 to go forward, what are we doing to go backwards? If we're adding 2 to go to the right, to go backwards, we're going to do the opposite, or subtract 2. So 3 subtract 2 gives 1. Subtract 2 gives negative 1. Subtract 2 gives negative 3. Subtract 2 again, we get what? Negative 5. Okay, so cross this out. This is called our imaginary. This is our imaginary y-intercept. Why do we call it the imaginary y-intercept? Because it's not even a point in the function. Why? Because 0 is not in the domain. Notice, if this were a point, we would have the point 0, negative 5. I want you to write that in the t-table, 0, negative 5, and cross it out. Why are we doing this? Why are we doing this? Because this point is going to save us a lot of time. So 0, negative 5, and now I want you to mark it on the graph. 0, negative 5 is here. Mark this location, circle it, put an X through it, okay, and write, not part of the function. Why is it not part of the function? It's not part of the function because what? Because 0 is not in the domain. Because the domain is just the set of natural numbers. 1, 2, 3, 4. We have a height at 1. We have a height at 2, we have a height at 3, and we have a height at 4, but we do not have a height at 0. Remember, what do we know about y-intercepts? We know that y-intercepts have an x value of 0. Notice, why is this a y-intercept? Because the end value, or the domain value, is 0. Well, I shouldn't say domain value. It's not even in the domain. 0 is not even in the domain. But if it were, the domain value would be 0. So what is the location of this imaginary y-intercept that's not even part of the function? Its location is 0, -5. So every time we graph arithmetic sequences, we are going to write this point that's not even part of the function as a sub 0, -5. Okay, but again, where does the function start? Here. This point is not part of the function. The function starts where? At a sub 1 equals -3, or at the point 1, -3. Okay? Now, I will show you why this point is so important in a minute. Cross it out in the t-table, okay? In fact, I almost erase it back out, I guess. I'm just going to erase it back out to emphasize this is not actually even a point. But in your notes, go ahead and leave it, well, I guess, leave it crossed out, for heaven's sake. Leave it crossed out. And then you guys understand that this is not actually part of the function. Cross it out on the graph, okay? But it's going to be important for saving this time. Now, over here, I'm going to erase. We know that our common difference is what? -2. Well, before I erase this, let's look. What is common difference? We think of common difference as what? Slope. Again, we're going to use linear function to understand this. So slope. To go from one point to the next, how far do we have to go up? How far do we have to rise? Remember, slope is what? M, or slope, is rise over run. Okay, so to go from one point to the next, we rise what? From a height of 1 to a height of 3 is a rise of 2. And a run of how far? A run of 1. So the rise is 2, the run is 1 to get to any point. Rise is 2, run is 1. So we say our rise is 2, run is 1. We have a slope of what? 2. Notice that the slope of 2 is the same as what? Common difference. Now, does this function have a slope? No. Slope is linear function. We don't call this slope, we call it what? Common difference. So if I say slope is 2, okay, I should say we don't say slope is 2. We don't say slope is 2. We say what? The common difference is 2. So when you hear common difference is 2, in your mind you can think, well, that's similar to saying slope is 2. Okay, so we don't call it slope, we call it what? Common difference. Now I'm going to erase this. I'm going to write d equals 2, and we think of this as what? In the back of our mind, we think of this as slope. Okay, so arithmetic sequence does not have a slope. It has what? A common difference. Okay, and the common difference is 2. Now, step 3 is to write the equation. Okay, the equation of this sequence. Okay, the equation of the sequence, just like we wrote the equation of a line. I'm going to erase this. Okay, we're going to write the equation of these points, or the pattern of the points. There's a pattern to this. The equation is, this looks quite complicated, but it's not that bad. A sub n minus a sub k equals d times quantity n minus k. Okay? And this should look, hopefully, familiar to you. Okay? Let me write underneath it. Do you recognize something here? I'm going to write down here y minus k equals m times quantity x minus h. Do you see the same thing? Okay, we call this what? We call this point slope form of what? Point slope form of a linear function. Notice y minus k equals m times quantity x minus h was our equation for point slope form of a linear function. Okay? A sub n minus a sub k equals d times quantity n minus k is similar to, we can think of this as point slope form for arithmetic sequence. Okay, and just like for linear function, we needed what? We needed a point and we needed a slope. Same thing for arithmetic sequence, except we're going to say that we need a point and we need what? A common difference. Okay, I'm just going to write common, well, I'm going to write a common difference. Or just here, just variable d. We need a point and we need a common difference. Okay, so let's just give an example here. Give me a point over here. So we say, we got to practice for a minute. We said a sub n was height at n. Do we write, yeah, I'm just going to erase some space here. We need some space. Okay, so do we write points as, well, if we say a sub 3, let's say a sub 3 is what? Height at what? 3. Okay, so this takes some concentration here to try to read this. A sub 3 is height at 3. Now, what is the height at 3? The height at 3 is what? Height at 3 is equal to 1. Okay, we read this as the ordered pair 3, 1. But what do we write? Do we write the ordered pair 3, 1, or do we write a sub 3 equals 1? We write, for arithmetic sequence, a sub 3 equals 1. So your reading points is a sub 3 equals 1 is the point 3, 1. You're not actually writing the point as 3, 1. So for instance here, if I said the point 4, 3, you do not write this as 4, 3. You write this as what? A sub 4 equals 3. And we read this as the point 4, 3. Now, also, this is, here, catch this. So we say a sub 4 equals 3. It's kind of, let's see if I can bring this out. Let's look at here. If I write, this is not what we write, 4, 3. Let me make this a sub 4. Okay, so a sub 4 represents what? A sub 4 represents height at 4. So if I write the point 4, 3, you read this as what? A sub 4 is equal to 3. Now my question is, what if I wrote here 4, comma, what? 4, comma, what? 4, comma, a sub 4. Okay, so if I write 4, you can just write 4, comma, a sub 4. What are you saying? Well, isn't a sub 4 the same as 3? So if I write this here, if I write 3, comma, say you didn't know this. You didn't know, or you could not see the sequence range. Okay, so if I write 3, at 3, what is the height at 3? At 3, the height at 3 is a sub 3. At 2, what is the height at 2? At 2, the height at 2 is a sub 2. Okay, so we're seeing, notice, well, here, if I were able to give you the range, you could look at the range, you could say, oh, there it is. We say what? We say 3, and what is the specific height at 3? The height at 3 is what? 1. Do you guys see that a sub 3 is the same as what? A sub 3 is the same as 1. So at 2, what is the height at 2? At 2, what is the height at 2? If you can see it, you can tell me. So at 2, the height at 2 specifically is what? Negative 1. So and my question is, what about k? What about k? If you don't know what k is, well then what do we say the y value is? The y value is a sub k, or height at k. So over here, for our equation, we say the point is what? The point is k, what? Height at k. Point is k, height at k. Now, before I confuse you further, let's just do this one more time here. Say it again. So if the point is 4, 3, you see that this could be written as 4, comma what? Height at 4. Okay, 4, height at 4, because we see height at 4 is 3. So, again, we don't write ordered pairs this way. So if I say 4, what is this? 4, we have what? Height at 4. Okay, and if I say, what is the specific height at 4? The specific height at 4 is what? 4, comma, what? 3. So you can just see, looking at the range, the height at 4 is what? 3. But again, we don't write 4, 3. We don't write 4, comma, 3. We just write what? A sub 4 equals 3. Okay, so just trying to get you used to looking at this notation. Now at k we are what? Height at k. Notice in the point slope form we had what? Point was hk. I want you guys to notice something. The k value, and these are different k's, so I don't want you to get confused. This k is different from this k. But notice, where did the k value go? The y value went what? The y value went next to y, and the x value went next to what? X. Notice in the point slope form equation, do you see that instead of x, in the point slope form, in the arithmetic sequence form, instead of x, we're using what? N. Notice over here we have n. Okay? Instead of y, we are using what? Instead of y, we are using a sub n. Notice the y-axis is called what? A sub n. Also, I want you to notice, instead of slope m, we're calling this what? We're calling this d common difference. Now, also I want you to notice h was the value that went next to x. Notice that k is the value that goes next to what? X or n. Okay? And also our k value or our y value went next to what? Went next to y. And it was the opposite. Our y value, a sub k, goes next to what? Goes next to the y value, or the y variable, a sub n. Now, for example, give you just a little quick, pick a point. Here, I'm going to erase this. Just show you how to do it. Okay, so pick a point out of here in this sequence. How about we pick the point 4, 3, something other than the first. The point 4, 3. So, for instance, with linear, you would have said the point was 4, 3, and the slope was 2. Well, we know our slope here. Okay, slope concept, if this were a line, slope would be 2. Okay, so we would put what? The y value next to y, and we would say that the equation was what? Start with y, opposite the y value is what? Negative 3, equals what goes next? Slope goes next. Slope is 2 times quantity x. Then opposite the x value is what? Opposite the x value is what? Negative 4. Again, this is how we wrote our point-slope form. Now, with the arithmetic sequence, you're going to write it like this. Instead of writing it 4 comma 3, you're going to write it as a sub 4 equals 3. And we read this as the point what? 4, 3. Now, also, I guess for the homework, if you need to do this, 4 comma 3, that's fine. But I want you to get away from writing points as 4 comma 3. But how do we write points for sequences? We write points as a sub 4 equals 3, and you read this as 4, 3. Okay? Now, we also have a common difference. A common difference of what? 2. So we're going to write the equation as start with our y, or in this case, start with a sub n, then opposite the y value. What is the y value? Okay, or a sub n value is what? 3. This goes here. Opposite of 3 is what? Negative 3 equals, we put our slope, or in this case, common difference next, which is 2 times quantity. Instead of x, we're using what? Instead of x, we're using n. Then opposite the n value. What is our n value? N value is what? 4. So the opposite of this is minus 4, and it's the same process. So a sub n minus 3 equals 2 times quantity n minus 4 is your equation. Okay? All right, if you are struggling to understand or see this, don't fret. I'm going to show you a simple way to do this, but for now I want you to get comfortable, or at least try to get comfortable writing what we call, think of this as point-slope form of the arithmetic sequence. Now, over here our equation is, I'll do it one more time. Here, we picked any point. It doesn't matter what point you pick. So we said the equation was a sub n minus a sub k equals d times quantity n minus k. We said that our point we picked was what? Height at 4 is 3. So a sub 4 equals 3. Common difference is 2. You put the y value 3 here next to y. So we say a sub n is our y. Opposite the y value minus 3 equals the slope goes next, or the common difference 2 times quantity, not x. We're using n. Okay? N, and then opposite the n value goes here, which is what? Opposite of 4 is negative 4. Now, you have to convert this. This is concept of point slope. We're going to convert this to slope-intercept form, or similar to slope-intercept form. It's not called slope-intercept form, but the form of the equation that we want to get to is similar to slope-intercept form. I want you to distribute the 2. So we get a sub n minus 3 is equal to 2 times n is 2n. 2 times negative 4 is negative 8. And now move the negative 3 to the other side. Okay, negative 3 will become what? Plus 3. Cross it out. We get a sub n equals 2n and minus 5. And I want you guys to notice you are looking at what? Y equals mx plus b. Y equals mx plus b. Notice instead of y we're using what? Instead of y we're using a sub n. Instead of x we're using what? Instead of x we're using n. And our slope is called what? Common difference. Our common difference is 2. Okay, so notice it's all the same. And notice, what is that imaginary? What is that imaginary location of the y-intercept that's not actually part of the function? If there were a y-intercept, it would be located where? At 0, negative 5. Notice negative 5 and what? Negative 5. Now, this is what I was going to get at. This is what's going to save us a lot of time. So let's go ahead and see, why did we write this point? Okay, so let's go ahead and make sense of the importance of a sub 0 is equal to negative 5. Okay, so you guys will get tired of these steps very quickly. To write the equation, it's unnecessary to go through all these steps. For tonight's homework, I want you to practice this. Okay. However, soon we're going to save a lot of time by writing underneath this imaginary y-intercept. I want you to write y equals mx plus b. And same concept, just like we need a point and slope for linear function, we need point and slope for arithmetic sequence. Notice, y equals mx plus b is the slope-intercept form of a line or a linear function. Notice we're going to just substitute in, instead of y, we're going to substitute in what? A sub n equals, okay, instead of m or a slope, we have a common difference of what? Common difference of 2. Instead of x, we're using what? We're using variable n, so 2n. And instead of b, what is the location of our imaginary y-intercept that's not actually part of the function? If we did have a point at a sub 0, that location would be negative 5. So write minus 5, and you see you can write the equation of the sequence very, very quickly without having to go through these steps. Okay, so this is what we're going to be doing soon. Just looking at the imaginary y-intercept and writing the equation of a sequence. For instance, watch. So if I give you a sequence, watch. 3, 7, 11, comma, dot, dot, dot. This is a sub 1, a sub 2, a sub 3. What is that imaginary y-intercept a sub 0, if it did exist? Notice to go forward is to what? Add 4. 3 plus 4 is 7. 7 plus 4 is 11. So to go forward or go to the right is to add 4. So to go backwards would be to do what? Subtract 4. 3 minus 4 gives what? Negative 1. Circle this, cross it out. That's your imaginary y-intercept. And you can write the equation of the sequence, y equals mx plus b, very quickly as what is y? What is y? Well, y is represented by variable a sub n. And what is our slope or our common difference? That's what's being added to go forward. What is being added to go forward? 4. So we write 4. Instead of x, we use what? Instead of x, we use n. And then our imaginary y-intercept, in this case, was what? Imaginary y-intercept is negative 1, so minus 1. And a sub n equals 4n minus 1 is the equation of the sequence. And we're done. Okay, so that's going to be the process in the next lesson or the lesson after that. We're going to switch to that process. All right, so your equation is a sub n equals 2n minus 5. I'm going to erase this because we're going to need the space. So a sub n, so common difference, was d equals 2. We found that as step 1. And step 3 was the equation. Okay, and our equation is a sub n equals 2n minus 5. And what is the equation useful for? Well, the equation is useful for generating very large range values. So notice, height at 4 is 3. Okay, my question is find the height. Here, write this. Step 4 will be tonight, find the height at 50. Okay. Well, if a sub 4 represents height at 4, and a sub n represents what? Height at n. Okay, what is height at 50? Okay, height at 50 will be what? A sub 50. And notice, height at 50. Well, we know the height at 4 is 3. And if we keep going in this pattern, the height at 5 would be what? Height at 5 would be 5. Height at 6 would be 7. The height at 7 would be 9, and so on and so forth. But do you want to continue doing this pattern all the way to the height at 50? No. Okay, so the equation is what you're going to use to calculate this height at 50 very quickly. The equation is used to generate large range values very quickly. So underneath height at 50, I want you to write a sub n equals 2n minus 5. Okay, this is our equation we're going to use, and we are finding height at 50. So underneath this, write a sub 50, which means height at 50. And I want you to notice, what is replacing n? What is replacing n? 50 is replacing n, so we're going to have 2 times what? What's replacing n here? 50. So 2 times 50. Notice that 50 is replacing n here, 50 is replacing n here. So 2 times 50 minus 5, which is 100 minus 5, or 95. Okay, so our height at 50 is equal to 95. And we read this, but we don't write this. Okay, we read this as what? The point 50, 95. We read this as the point what? 50, 95. Or the height at 50 is what? 95. Okay, height at 50 is 95. Now, just to get you guys, you've already seen this. Okay, so if we say a sub 4 is height at 4, okay, soon we're going to be going back and using that f of x notation that I talked about. So a sub n is what? Height at n. Okay, what if I wrote f of x? I'm sorry, f of 2. What if I wrote f of 2? Going back to function notation for a minute, you've seen this before. I told you to think of f of x as y dressed up in a suit. Okay, so f of 2. What is f of 2? Well, f of 2 will mean height at what? Height at 2. And what will f of x mean? F of x will mean what? Height at x. Okay, so there's going to be similarity between sequence notation and functional notation f of x. So f of 2 will mean height at 2 and f of x will mean height at x. That's coming. All right, now, okay, so step 4 is height at 50, and then step 5 is to write the series. Okay, so before we do step 5, I'm running out of space here. Okay, so step 5, I'm going to just erase. Let me do this. You can always erase the video. I'm sorry, you can always rewind the video. So I'm going to erase all this. Okay, now we're going to look at new topic. Okay, new topic. But this is tied in. Okay, step 5 will be to find the sum of the first 5 elements. Now, from the definition, we've said element means, or definition of function, we said that element means what? Element means number. Okay, so the first 5 elements is the first 5, no, I'm sorry, let's make that 10. First 10 elements, or the first 10 numbers of the range. So what are you doing here? You're adding -3 plus -1 plus 1 plus 3. You're adding the first 10 numbers in the range together. We call this a series. What is a series? Okay, so in this case we're going to say, well, let's define series. A series is the sum, go ahead and put this in your definition sheet, on your definition sheet. A series is the sum of the set, of a set, of range elements of a sequence. A series is, here, let me change here, definition of series. A series is the sum of a set of range elements of a sequence. So this is called, here, this is called definition. This is called the definition of a series. Okay? And since we are looking at an arithmetic sequence, this series will be called, this series to find the sum of the first 10 elements of the range, since this is an arithmetic sequence, will be called an arithmetic series. Okay, so series is very simple, very simple. It's a value, okay? It's the sum of the range elements of a sequence. So what is a series? What we're going to be doing is taking this range. We're going to be taking this range, -3 plus what? -3 plus -1 plus 1 plus 3 plus what's the next number? The next number is 5 plus what? Plus 7 plus, and we're going to keep doing this till we get to the 10th number, plus 9 plus 11 plus 13, 1, 2, 3, 4, 5, 6, 7, 8, 9 plus 15. We're going to add all these up and we're going to get 60. Okay, so we have, there's a trick here. I'm going to show you how this works, but you get what? 60. You can add all these numbers up. Okay, so we're going to add these up. And we're going to get 60. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, so we get 60. Now, how do we write this? So definition of a series is this. A series is the sum of the set of range elements of a sequence. Make sure this is on your definition sheet. I'm going to erase this, and let's talk. So you have to write the series in sigma notation first. Okay, so let's define some symbols here. This is sigma, capital sigma. The name of the symbol is sigma. Now, you guys have seen sigma before. Sigma, you've seen lowercase sigma. Lowercase sigma represents population standard deviation. Lowercase sigma is population standard deviation referring to normal distribution. This is capital sigma, okay? And capital sigma means what? Capital sigma means add. That's all it means. Sigma means add. Okay, so to add, what are we adding here? We're finding the sum of what? Finding the sum of the range. Finding the sum of the range. So we are adding what? We have to add the range. Now, since sigma means add, I'm going to write this. Sigma means what? Add. We need to add what? We need to add the range. But before we do this, you need to understand how to write the range. So looking over here, okay, again, we have to be careful here to understand these symbols. Okay, so if I write a sub 5, we read this as what? Height at what? 5, okay? And if I say a sub n, we read this as what? Height at n. Hopefully you've gotten this already. Now, notice, here, let's do height at 4. Okay, so height at 4, height at 4. Okay, so now I'm going to write, what is the height at 4? The height at 4 is what? We read this as height at 4 is 3. So a sub 4, height at 4 is what? 3. Now I want you to circle. I want you to circle the 3. Okay, is 3 part of the domain of the range? Is 3 part of the domain of the range? Hopefully you say 3 is what? Range. Now, notice the equality. By the reflexive property of equality, we can say that what? Range equals what? Circle a sub 4 and write range. Okay, circle a sub 4 and write range. You guys agree range is equal to what? Range is equal to range. Now, So we see that a sub 4 is a symbol for range. So when you see a sub 4, what do you think? A sub 4 represents what? Range. Why is a sub 4 such a beautiful notation? Because notice, you see a sub 4, the entire symbol is what? Entire symbol is range, but what is the 4? The 4 is what? The 4 is domain. Notice, 3 is the range, but 4 is the domain. Notice down here, 1, 2, 3, 4. These were the domain values. So do you see range and domain in the same statement? Yes. If I write a sub n, what is a sub n? A sub n is what? Range. Okay, what is the n? The n is what? Domain. So in the same symbol, you see what? Domain and range. What if I write f of x? What if I write f of x? F of x represents what? Range. And what does the x represent? X represents what? Domain. So in the same symbol, you see domain and range. Why is f of x a better symbol than y? Why is f of x a better symbol than y? Because y, you just see what? Y, you see range. Remember that f of x is a symbol for y. You just see range, but you don't see domain. F of x is a better symbol because we can see what? Range and domain in the same statement. Now, so going back to this, we say if we write a sub 4, again, a sub 4 is equal to what? 3. We see 3 is range. We see what? A sub 4 is range. And if I write a sub n, we see a sub n, this symbol is what? Range. Now, looking at the equation, look at the equation, a sub n equals 2n minus 5. I'm going to write this a little bigger. A sub n equals 2n minus 5. I want you guys to notice, what is a sub n a symbol for? A sub n is a symbol for what? Range. So circle a sub n. And I also want you to notice 2n minus 5. Notice range is equal to what? Range is equal to range. A sub n is very general. A sub n represents any range. A sub n represents the range of any sequence. But however, what represents specifically this range? So we want to be more specific. If I say, okay, all right, what are you? Okay, who are you? Who are you? Okay, if I say be specific, who are you? This is a good example. Or what or who are you? You say, well, I'm a human being. Okay, well that's not very specific. But who are you? You are so and so. Okay, so to me, okay, I'm a human being, but more specifically, I am David Thaxton. That is me. That is specifically me. We want to be more specific. Okay, so range. A sub n is very general. Okay, that's I'm a human. Okay, that's general. I'm a sequence. Okay, but what is 2n minus 5? 2n minus 5 is I am this specific sequence. It has a name. What is the name of this sequence? That's my name. My name, okay, I'm a human. That's a sub n. That's range. Okay, I'm a human. That's general. Okay, I'm a sequence. Okay, but 2n minus 5 is specifically who am I? I'm David Thaxton. That's specifically who I am. So what's the name of the sequence? Okay, you can say that this range, generally, a sub n is any. Okay, but what's specifically the name of this range? The name of this range is what? 2n minus 5. So 2n minus 5 is a specific name for what? This range. Okay, so how do we represent this range? So what are you trying to do with series? All this to say, what are you trying to do? You're trying to what? Add the range. So you're trying to do sigma what? Sigma a sub n. Okay, isn't range represented by symbol a sub n? Yes, but this is very general. We want to add that range specifically. So we're not going to write sigma a sub n. What are we going to write? Sigma, here, adding range, adding a sub n. Okay, we write sigma, what is specifically the name of this range? 2n minus what? 5. Okay, so do you see add the range? Or add specifically this range? Okay, so I want you to write on your paper. Okay, so when you see find the sum of the first 10 elements of the range, borrow this 2n minus 5 or whatever this expression is in your equation to the right of a sub n. We're writing sigma, which means add. This specific range is what? 2n minus 5. So we read this as what? We read this as add what? The range. And we're adding what? The first 10 elements of the range. The first 10. Okay, so the first 10 will be from n equals 1 to 10, and we think of this as a step ladder. So we're putting in 1, we're putting in 2. So think of this as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the domain. Okay? This is the domain from 1 to 10. Okay, so we're adding what range numbers? The range numbers that are associated with these domain elements, 1 to 10. So the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th. So 1 to 10 is your domain. 2n minus 5 is your specific range. Okay, and we're adding what? We read this statement is read is add the first 10, add what? The first 10 elements of the range. Okay, add the first 10 elements of the range. Now, to do it, just simply write them out. Just simply write them out. So we're writing what? Negative 3 plus what? Negative 1 plus what? 1 plus 3. And you see the pattern. The pattern is that you're going up by what? Going up by 2, so just write them all out. So 3, then what? 5, then 7, then plus, here, plus 9, plus 11, plus 13, plus 15, and that should be all of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and simply add them up. Okay, so if you need, do it by hand or get a calculator, add them up. Okay, we get 60. All right. Yeah, we get 60. All right. Now, and there's a trick to this I'm going to show you. So that concludes this lesson. For tonight, you have 5 steps. Okay, step 1 is to find the common difference. Step 2 is to graph it. Step 3 is to find the equation. Step 4 is to calculate height at 50. And step 5 is to find the sum of the first 10 elements of the range. Remember, to find the sum of the first 10 elements of the range, we call this what? Series. And since this is an arithmetic sequence, we call this an arithmetic what? An arithmetic series. So if you circle this, what is this? This is a series. And what type of series? It's an arithmetic. Okay, it's an arithmetic series. And what is, okay, so if we circle this, this is arithmetic series. This is arithmetic series. And what is 60? What is 60? 60 is also an arithmetic series. You can think of arithmetic series for now as just a value. The definition is that a series is the sum of a set of range elements of a sequence. All right, that concludes this lesson. Great.